We all kind of have this simple picture in our heads of how AI works, right? We think of a little neuron inside the machine that just lights up when it sees a cat or when it hears the word justice. It's a neat idea. But what if that simple story, as helpful as it seems, is actually what's stopping us from getting what's really going on in there? So yeah, let's dive in.
So let's get right to it. The big question for today is, how does an AI really think? We're going to push past those simple stories and take a look under the hood at the messy, way more complex, and honestly far more fascinating reality of how these things actually represent our world.
All right, first, let's talk about the idea that we all find so intuitive. It's the feature detector. This is pretty much our go-to mental model, and you know what? There's a good reason for that. The whole idea is that for any concept you can think of, there's a neuron, or maybe a little cluster of them, whose whole job is just to spot that one thing. It's a super clean, very satisfying picture, isn't it? A neuron for code, another for an angry tone, another for legal jargon. It's like a perfectly organized library where every single idea has its own dedicated shelf. And to be fair, this isn't totally made up. Researchers really do find neurons that are shockingly specialized like this.
But, and this is a big but, this is exactly where that simple story starts to break down. As one of our sources says so well, the trouble begins when we imagine the whole network works like a tidy museum in which every neuron has a plaque under it. The problem isn't that these feature detectors don't exist, it's that there is no way the entire network can work like that. The reality is, it's a lot more crowded in there.
So why can't it be a tidy museum? Well, it all comes down to a fundamental bottleneck. It's basically a real estate problem. There's just not enough space. And this slide really nails the issue. On one side, you have a practically infinite number of concepts, words, styles, and ideas that an AI needs to understand. I mean, it's countless. But on the other side, you've got a very finite, very limited number of neurons in any given layer of the network. You can see the conflict, right? There just aren't enough plaques to go around for that museum. So what happens? This conflict creates this incredible pressure. The network is basically forced, just by how it's built, to figure out a way to represent this huge world of ideas using a very limited toolkit. It has no choice but to get really, really efficient.
And this constant pressure for efficiency, it leads to a really beautiful and complex solution. Instead of trying to keep every concept in its own little box, the network learns to let them overlap.
The first big idea here is called superposition. This is the network's main trick for cramming more meaning into the exact same space. It pretty much decides, nope, I'm not giving each feature its own private neuron. Instead, it packs them together into these messy, overlapping patterns.
Okay, let's make this even simpler. Forget neurons for a second. Just picture a really crowded room. You can't give every single person their own private corner, right? You'd run out of space in a second. But if people can kind of overlap and share the same general area, you can fit way more of them in. Superposition is just like that, but for ideas instead of people. Now, a direct result of all this overlapping is something called polysemanticity. It's a fancy word, but it just means that a single neuron can end up doing multiple jobs. Because all these ideas are sharing space, one neuron might find itself responding to several different and seemingly unrelated concepts. As the source puts it, it's not monogamous with just one meaning. So what does this actually look like in practice? Well, you might have one neuron that fires for things that, to us, look totally random and unrelated. It might light up for citation patterns in academic papers, but also for scientific notation and maybe even for a certain formal, argumentative tone. From the neuron's perspective, these different patterns all share some kind of underlying quality that makes them similar enough to trigger a response.
Okay, so if the inside of an AI is this messy, overlapping, multi-purpose system, how on earth does it all come together to produce something that actually makes sense? How does this chaos turn into coherent thought? Let's take a look.
The first big mental shift for us is to stop thinking about a key part of the network, the MLP, or multi-layer perceptron, as just a simple bank of detectors. It's not just sitting there saying, yep, I see a cat, or nope, no cat. It's an active mixing system. It's constantly taking in these messy signals, turning some up, turning some down, and blending them all together.
And look at how this whole process works. The AI doesn't just find the perfect meaning in one shot. It's a cycle, a refinement process. First, a really messy, overlapping pattern gets activated. Then, the network makes a small, partial update, just a little nudge in a more useful direction. Then other parts of the model jump in and add context. The result is a slightly sharper, more refined meaning. And this happens again and again and again, layer after layer.
And the thing that makes this whole step-by-step process possible is something called the residual stream. You can think of it as the AI's working memory, but it's actually more than just storage. As the source material puts it so perfectly, it carries semantic momentum. It remembers the progress of this clarification, which allows each new layer to build on the work of the one before it.
So if our old mental model, the tidy museum, the filing cabinet, if that's just wrong, what should we replace it with? We need a new, more accurate image for how these systems actually think.
Here's the shift we need to make. We've got to move away from the image of a filing cabinet with all its neat, isolated little drawers. A much, much better image is a musical instrument. An instrument has a shared structure, right? And the music it makes comes from complex, overlapping resonances and harmonics.
Let's really lean into this musical instrument idea, because it's a great one. Think of the AI's knowledge, all those weights it learned during training. That's the actual physical instrument itself, the wood, the strings, the whole structure. Now, the prompt you give it, that's you striking a chord. That's the initial vibration. And the AI's thought process, all those activations firing away, well, that's the music. Those are the rich, complex harmonics that actually ring out and create the meaning.
This final quote from the source just nails this new image. We shouldn't be picturing a wall of on and off switches, each with a neat little label. We should be picturing a vast, crowded cathedral, filled with all these resonant parts that vibrate together in these incredibly complex, overlapping patterns to create meaning.
Look, this isn't just about finding a cooler metaphor. It fundamentally changes how we think about what an AI is even doing when it thinks. And it leaves us with this one last really provocative question. If an AI truly is a cathedral of resonance, what kind of music is it actually learning to play?